Okay, hi everyone and good morning. My name's Sonia Heaven from the University of Southampton. Well, I'm reporting on work by a team of myself and my colleagues. I'm also the director of the Environmental Biotechnology Network and a co-investigator on the Carbon Recycling Network. And I hope you'll see why this presentation is relevant to both. So we're talking about balancing hydrogen input to anaerobic digesters. And just to start with a little bit of background, the underlying process for this purpose is the ability to convert carbon dioxide and hydrogen into methane. And obviously that's something that has a lot of attractions. As you're all no doubt aware by now, we sometimes produce more renewable electricity from photovoltaic and wind than we can use. One way of storing that is to convert it into hydrogen through water electrolysis. And you could stop there. Hydrogen may, in the long and medium term, be the right solution. But at the moment, our infrastructure is a lot more compatible with methane. And there are other reasons why methane is a good answer. I don't have to tell this audience that. Obviously, it also offers the potential for capturing CO2 and utilizing it. And that's very attractive for big CO2 sources like power stations, cement kilns, yes. And you can carry out this process. It's been known for well over 100 years, the Sabatier reaction by thermochemical means, but it takes a lot of temperature, a lot of pressure. The biological route for doing it is therefore very attractive because microorganisms can effectively do it at local temperature and pressure. And that's a whole interesting topic in itself. Again, just quick coverage because you may well be aware, but there are two main approaches used, and they're often referred to as ex situ, which means we're using feedstocks that are gases. Microbes actually take the hydrogen and carbon dioxide and convert it, or in situ, where we have an anaerobic digester fed on an organic feedstock, and that converts. By adding hydrogen, we can convert some of the CO2 in the biogas. That's the process of interest. At the moment, ex situ processes with gaseous feedstocks are tending to get a lot more research and commercial attention, and there are good reasons for that. They have this wider application to sources of CO2 from power stations and so on. And they have the potential to be very high rate to deal with really large emitters, yeah. We're interested in them, we're working on them, but our group really wants to put in a plug for thinking more about in situ, because that may actually have an important role too via the use of existing anaerobic digestion infrastructure. However, the other reason that in situ is less popular is that historically there have been some concerns over the stability of the process. Is it easy to crash your digester because of sudden shifts in the pH, in the acidity of the reactor? Basically, the issues boil down to the fact that if you are converting the CO2 that's present in the biogas into methane, then the system will lose buffering capacity and the pH of the digester will go up. Over a certain pH, the organisms that produce methane can't cope. The process is inhibited. That means you start to get a buildup of VFAs, and as digester operators know and fear, that can actually lead to a pH crash and potential failure of the digester, very expensive if you're operating a full-scale plant. So I've got a few results here from some early work we did. The graph shows pH on the y-axis against time on the x-axis, and we were basically adding slowly and cautiously in those days, increasing amounts of hydrogen to convert CO2 present in the biogas. And we took that value up 10, 20, 30% and so on. And then finally we took it up to 100%, and you can see what happened. The pH did a sudden big jump, very uncomfortable change of conditions for the microbes. And there were signs of instability, and we hastily took it down again to about 95%. And at that point, we could get some much more stable operation at a pH that we felt was acceptable. And if you look at the same data, but plotted on a graph where here we've got the pH going up the y-axis and the amount of CO2 we've converted, how much hydrogen did we add, if you like, You can see why. The curve is actually very sharp. It's a logarithmic curve. Once you get up to a high pH, in other words, you've got very little CO2 left in your biogas, only a few percent, then the curve is really steep and it's difficult to control it. Okay, so we thought we need to understand this relationship better. If we're going to have biogas with a high methane content, how can we safely control it and not risk crashing the digester? So we carried out a lot of experimental work, and I'm really doing a quick summary here today. But we looked deliberately at 3 different types of feedstock or substrate. We looked at a synthetic one, because there we could control the amount of the total ammonia nitrogen, TAN, that was present. And we know that that is important in affecting the pH and other reactor conditions in anaerobic digesters. We also looked at industrial food waste and at sewage sludge, because those are 2 big commercial feedstocks in the UK industry worldwide. And basically the methodology for all the experiments was pretty similar. We ran some kind of a baseline or control digester without hydrogen addition, just to see how it was behaving without this. And then in a pair of experimental reactors, we would progressively add hydrogen, and we'd monitor and measure the pH, the gas composition, and the amount of gas produced, and a whole string of other parameters. And I should mention that a lot of this work was done in a project, an IB Catalyst funded project known as H2AD, funded by the Engineering and Physical Sciences Research Council. Okay, so some results using synthetic feed with a controlled nitrogen content. We ran the experiment for about 120 days. I haven't shown it there, but just to get stability and a baseline. Then we started adding hydrogen incrementally to one of the pair of digesters. I hope you can see the dotted line is where we started adding hydrogen, and then we have increasing hydrogen addition. So we're converting more and more of the methane. You can see that the pH curve is kind of following the rise in methane percentage, the reduction in CO2. And the graph at the bottom is showing you what's the methane productivity of that digester, in this case in litres of methane per litre of digester per day. And over that period, you can see it's gone from being about 0.75 to roughly doubled to 1.5 litres of methane, still receiving the same organic feed, but we've just converted most of the carbon dioxide in the biogas into methane. We then over-egged it a bit. We let the pH go a bit high. We had slightly too high methane content, and actually that disturbed the reactor. The biogas productivity fell. It took us a little while to stabilize it. Well, clearly, if you're running a big commercial reactor, you can't afford that, so you do need this better knowledge. However, we thought we'd learned a lot from it. So after running that experiment for about 280 days, we took the pair that had been operating, the pair of reactors that had been operating as controls, and repeated this hydrogen addition. And as you can see, we'd got very confident then. We'd got kind of, we could do it much better, much smoother results. Okay. We did a similar thing for the digesters on the same feedstock, but with artificially a higher TAN concentration and therefore higher pH. And I hope you can see from the graph on the right, we were getting quite cocky, quite confident. We started to be able to draw nice V shapes and W shapes whenever we wanted by increasing or decreasing the hydrogen content, and therefore increasing or decreasing the biogas CO2, the biogas methane. We did a similar trial in a digester fed on food waste, and that was a commercial feedstock very kindly provided by Malibu Biogas. And we were interested in that because food waste already has a high pH content. It's got a lot of TAN in it. Now, the previous reactors had started to cough, to stall at about pH 8.2. Food waste reactors often have that as their baseline value. So we were a bit nervous. Can we actually add more hydrogen? Will that cause a problem and drive the pH up even further? So we have a graph again, percentage of methane and the pH. We increased the hydrogen addition much more slowly because we were a bit nervous. But we eventually got it until we got to about, we were overconfident, we got the pH up to about 8.5, 8.6. At that point, there were signs of distress, so we had to fairly rapidly reduce it and bring down the methane content. So again, we decided that, okay, we've really got to understand this if we want a way to operate commercial digesters, and we need to look in more depth at the relationship between pH and the partial pressure of CO2. In other words, the amount of CO2 you've left there in your biogas after you've converted some of it to methane. And to cut a long story short, a colleague of mine, Dr. Yue Zhang, did some really insightful and, I would like to say, brilliant work looking at the theoretical basis for this relationship. She's the first person who's done it. I'm not proposing to explain it. If you're interested, we have a paper out on this. You can look up the details. But basically, she came up with a relationship between pH and the residual CO2, the partial CO2 pressure, based purely on theory. And there it is, the equation in all its glory. The question is, what's the big fuss? Well, if you look at that equation for a minute, you can see there are actually only a couple of parameters in it. It's got pH, it's got partial CO2, and it's got a factor A, which itself only contains some physical constants derived from theoretical considerations, and then those two parameters, pH and CO2. Now, those are things that are routinely measured. Even a large plant has got an idea of its biogas composition and either does measure the pH of its digestate, or if it doesn't, it can do it very cheaply and very simply. It's not a big, complicated ask, yeah. So effectively, if we know the baseline value for one point to give us this parameter A, and that point could be your normal operation of AD, your existing digester at a wastewater treatment plant or a food waste digester or whatever, then that allows us, using this equation, to predict the behavior of pH shift and therefore the likely maximum safe methane content and how much hydrogen you need to add to get there. It's actually a little bit more complicated than that. This equation was derived assuming that the pH is predominantly controlled by the ammonium carbonate buffering system. For most real organic feedstocks like food waste, cattle slurry, sewage sludge, that's true, but there are other buffers systems that could contribute, for example, phosphates. It also assumes that the TAN concentration remains roughly the same when you increase the methane. There are circumstances where that might not be true, but in both cases we found a fix. So again, if you're interested how, I can refer you to the paper. But we have a relationship. So if I go to the graph of those three trials, the food waste digester on the top, and then two different synthetic feeds or two similar synthetic feeds differing only in their nitrogen concentration, you can see there is a graph there that shows the CO2 along the x-axis, the pH up the y-axis, and something similar is happening in all three cases. But just looking at the data, it's hard to say, well, how do I know? How's it going to vary with feedstock? If we apply that same theoretical model to all three, you can see we get really good agreement. Very impressive performance. Now, we know we're working in an industry that's very conservative and risk averse. So we thought we'll come up with another belt, braces, and a piece of string to hold your trousers up, if you like. So we came up with something, a rapid determination system. And this is a really simple method. You take a sample of your existing digestate from your digester, you circulate biogas that has different proportions of methane and carbon dioxide in it, and you measure the pH with each of those. So it might be 60-40 methane carbon dioxide, 70-30, 80-20, and so on. And you then look at those and see how they relate to the theoretical prediction. So if we go back to that previous graph, the large dots show the results of this rapid determination system compared with the theoretical model and then the operational data from these very long-term experiments, hundreds of days that we ran in digesters. I think that's a really impressive result because you have to remember the rapid determination, nothing is equilibrated, no microorganisms have adapted or adjusted. We're just altering the system by changing the proportions of methane and carbon dioxide present in the biogas. So it gives us a bit of security, a feeling that this really works. Okay, so these methods I'm really impressed with them because they allow us to predict the maximum safe methane content for stable operation where we're not going to worry about fluctuations in biogas content or pH. Yeah. And they let us work out how much methane, how much hydrogen we need to add to achieve this. And this is all purely based on knowledge of this relationship. There are still some interesting questions. If you were quick and picked it up, you'll have noticed that I said, okay, some of those reactors were stable up to pH 8.2, some up to 8.6. Why is that difference? Well, we have some ideas about that, and we'd like to do some more work on it. When would academics not like to do a bit more research? But that's the kind of thing, the relationship between the biology and the scale up, which the UKRI funded networks, EBNet and the Carbon Recycling Network, are keen to sponsor and support. That's what we're there for, to develop the knowledge relationship between deep science and real application. Okay, one more experiment, two, I guess. We said, okay, let's try sewage sludge, another major AD substrate. And we'll try, based on what we know, ramping up the H2 addition very quickly. We think we can predict the safe biogas methane content, so let's try it. So if you look at the graph on the right, we have methane content percentage on the y-axis, time, and over a 12-day period, we actually took that methane content from about 60% up to 90%. And to be honest, we could have done it quicker. Myself and you told the guy doing the experiment, no, too fast, you'll upset it. And you can see he stopped level off in the middle. But actually, he could almost certainly have gone up quicker because we knew how far we could go. And throughout that, we got a nice stable pH in a safe range for this substrate. So it could cope well with these conditions. And if you go over to this comparison again, you can see the rapid determination theoretical model and the actual data for that short experiment all looked good. Okay, nearly finished. I just want to come back again for 1 second to food waste and show you some really crazy data, if you like. This was a food waste digester, batch fed once a day in the laboratory. And we tried it in varying operating modes. So the upper graph shows you a period of 9 consecutive days. We'd run it for quite a long time in a sort of hybrid system where we were converting the existing biogas to a higher methane content by adding hydrogen, but we were actually pumping CO2, additional external CO2 and H2 in. So it was working in both in situ and ex situ modes and converting a big load. I could talk about the shape of that curve. You can see that at the beginning, the pH is quite low during the day. It increases because the digester is using up its source of hydrogen. But main point is to say, okay, it was operating stably in that mode. At the end of 3 days, 72 hours, we abruptly, with no transition, just said, okay, take out all the extra CO2 and hydrogen. We're just going to convert the CO2 that's present in the naturally produced biogas from that reactor. Different curve of pH. We've got organisms that can consume the available hydrogen very quickly, but really no disturbance. 3 days after that, we said, okay, now we're going to stop adding hydrogen altogether. So that might simulate a time when maybe there's no renewable electricity to use. Maybe your hydrogen generator is bust. You've gone straight from adding hydrogen, having 95% methane content, down to normal AD. Again, it adjusted very quickly over 1 day. So there were sharp changes in the pH, but because we understood the system and operated it in a safe range, we could run it stably, even in those quite extreme conditions. So I really just want to end with a plug for saying, don't forget in situ and hybrid AD. It combines the addition of hydrogen to an anaerobic digester can allow you to combine biogas upgrading and increased methane productivity. You're not merely getting 95 or 90% methane out of your digester instead of 60%, but you're actually getting that extra amount of methane. So you have increased the methane yield per unit of reactor volume. That, of course, is a way of supporting the decarbonisation of some of our big industries, waste management, wastewater treatment. If they produce more methane in this way, they can use that to offset fossil fuels. It also offers another route to utilising surplus renewables. possibly as a grid balancing mechanism in common with others. It can't do it all, but it can contribute. There's a really interesting possibility that if you integrate with local renewables, off-grid, small PV or windmill or whatever, you could improve the economics of digesting low energy substrates. So things like cattle slurry. If you could almost double the methane yield, would on-farm digestion be more economically viable? Where you've got some external CO2, maybe from fermentation processes, brewery, or maybe actually because you run multiple digesters on one site and you can feed all of the biogas through one retrofitted AD plant, you can have this hybrid process where the organisms are getting their nutrients and their conditions from the organic feed, but you're converting a large volume of biogas and upgrading it and increasing the methane content. So we think we now have enough knowledge to understand and control this kind of system. What we'd really like to do now is be going for pilot and demonstration scales. And we believe that in these conditions, in situ and hybrid systems fed on organic wastes do actually have a valuable role to play in power to gas. That's all I have to say on the subject for today, but very happy to discuss it with anyone later on or even after the expo. Thank you very much.
Hello, Sonia, that was great. Thank you very much. And I won't do any more talking because there's quite a few questions I noticed. So I think we should just go straight into the questions and see if you have the answers. So we have a question from Dr. Keithson. Great work. And let me just get out of my way. Great work. Have you tried abusing the system by having hydrogen fed based in the similar highs and lows that would come from renewable electricity? And
that's a great question.
I think, well, he actually followed up with, I think you answered the question. Do you still see asset utilization of an expensive electrolyzer still being a barrier?
Yes, two really great questions. Yeah, I mean, we have done some, very good word, we have abused our digesters a bit, but clearly there's a lot more we'd like to look at about shorter term changes matched to the, and in fact, our colleagues, partners in the University of Sheffield are continuing to work on that and looking at literally matching the operational digester operating pattern with the fluctuations you might get in hydrogen generation if you're following the national grid demand, if you like. Sorry, what was the other bit of the question? Was yes, we've tried abusing it. What was the second bit? Because I thought that was
sorry. So I keep on getting notifications that cover it. So, tried abusing the system by having hydrogen fed based in the similar highs and lows that would come from renewable electricity. Do you still see asset utilization of an expensive electrolyzer?
The electrolyzer. Yes. At the moment, a couple of years ago, electrolyzers of a suitable size were just not being produced. They were tended to be produced either very small for lab needs, producing hydrogen gas for analysis, or very, very large. I think electrolyzers at the moment are way too expensive. I have student projects regularly trying to look at, could you do an on-farm, design an on-farm system? But I think that a little bit mirrors the situation with, I don't know, microwaves 30 years ago or PV in the last 10 years. When they are rare items, they're expensive, but boy, can the cost drop if there becomes a global demand. So I would expect to see the cost of electrolyzers in the right size range for AD dropping if there really is this demand, if industry generates it.
Thank you. We do have more questions, so I'm just going to crack on through them, as it were. And we have, so I just want to check. So we have a question from Rohit. Sorry. What's the conversion loss of making renewable power and then H2 to make more CH4?
It's a very good question again. There is probably, I'm told by electrolyzer manufacturers that electricity to hydrogen is probably about 80% now. If you then convert the hydrogen into methane, there is a loss because if you go right back to that equation at the beginning, half of your hydrogen is getting diverted into water in this particular system. There are other ways of doing it, microbial bioelectrochemical systems that reduce that. But yes, probably goes down. The efficiency of that step is probably about, I think, 78%. Yes. How you get some of the power back because you're adding the carbon bond. Yeah. So it's not magic. It is a way of storing energy in the same way as a battery or a pumped storage system is, but there is an energy loss. And that's why in the long term, maybe hydrogen will win out when we have a hydrogen economy. But in this case, because of the capacity to get more out of the carbon that you put into an anaerobic digester, for every gram of carbon you put in, whether you pay for it if it's an energy crop, or whether you just have to handle it if it's sewage or waste, for every gram of carbon you put in, if you can almost double the amount of methane output, that can still be economically very attractive, especially if those renewables would otherwise not be stored and be going to waste.
Great. I know you can't see the kind of live discussion and the comments.
Yes, sorry.
No, it's the kind of the way the system's designed. So Keith followed up with Chinese are bringing the costs down. So I think that was more for the electrolyzers. And so, yeah, backing up your comments about.
Yeah, no, I don't think they maybe won't fall quite as dramatically as PV. And this is always going to be a subset. But I think we need I hate hearing people knock one area of renewables or sustainability to promote their own. The answer is, guys, we're going to need all of them. Yes. Yeah. And I do think that we can already see, as Keith says, there are definitely already price drops occurring in the last 2-3 years even.
Yeah, makes perfect sense. So I think we're going to have to, there's a couple more questions here. So just to give you some feedback, James Chong, he said, beautiful talk, Sonia, which is always nice to hear.
I should fess up and say that James was one of the partners on this, and though we didn't in this presentation cover the biology of the system, the work that they are doing at York to elucidate that relationship between the really deep science of microorganisms and the large scale stuff. It's a mutual admiration society, I'm afraid.
Well, it still counts. He did have a question, but I might move on to Les Gornell's question, who also said, wonderful presentation. I don't know if you worked with Les as well.
No, I admire him, but I know and admire him.
Oh, well,
that's a compliment. Thank you.
Lovely to hear then. So wonderful presentation. How much of the H2 is not used and appears in the biogas as H2, not CH4? Bear in mind you have about a minute left on this.
I'll be even less because we were operating, again, there are a lot of choices that can be made about how do you operate your digesters. Do you decide to store biogas until there's hydrogen available? Do you decide to store hydrogen and feed at a constant rate? Many decisions. We so far have tended to operate ours so that all the hydrogen is consumed because it does represent it's cost money or energy to make it. Yeah. So we have tended to operate it so there is almost none left. Sometimes we'll be wrong by 1 or 2%. For most purposes, that's not a problem because actually a little bit of hydrogen and biogas can help with combustion in certain purposes. We might need to review a whole set of gas standards because standards in the gas grids internationally are not consistent. They're very variable, but they're also very stringent. On another project, we were working with Volkswagen and SEAT, and they are saying that, for example, for vehicles, they're happy with quite much lower percentage methane content in the vehicle fuel. So a little bit of hydrogen probably doesn't hurt. You don't want to be putting a lot in because then you've got a large volume of biogas with not much burn power. That's it.
Lovely. Sonia, you are bang on time. So, thank you very much.
Okay, thank you.
Great.